Friends, you're welcome to my series Embedded Design in Electrical Power Domain. Today we are entering the part 6. So, what we have done so far, let us see. True RMS value, active power, which is VI cos phi, harmonic components, symmetrical components. We have done means what? We have seen how to interface these power entities with our embedded system, right? So you are able now to measure practically the true RMS value, the active power, and a variety of harmonic components and symmetrical components. Now we will do today apparent power, power factor, reactive power, and frequency, right? And you will need this information, these two things you will need in order to gather apparent power, cos phi, and Vi sin phi. Frequency will not require any of these entities. Here, in this case, we are using sampling theorem. Here, we are not going to use sampling theorem, okay? But here we do. Let us move forward. Here you see that apparent power is the product of RMS value of voltage and RMS value of the current. So you already know how to find RMS values of voltage and currents. So you can do this. You know the hardware involved, you know the conditions involved. So like adding 1.5 volts and so on. So you can do it. We can have a look at the picture. So if you want to have apparent power, what you do? Measure current, measure voltage. Remember to give 1.5 volt shift. And also remember to ensure that this voltage never exceeds 1 volt RMS. Okay. So here you have the waveform. This is the voltage and current waveform. This is voltage and this is current waveform. Now here you are not going to multiply samples of voltage and currents. No. We will first find the RMS value of voltage independently, the RMS value of current, then simply multiply them. That gives you Vrms into IRMS, which is apparent power. Coming back, so this is what you do. Then power factor. How will you know power factor? We know active power is Vi cos phi and apparent power is Vi. Therefore, cos phi will become Vi cos phi upon Vi. And you had done active power earlier and you had done apparent power now. I mean, you are going to do this. Actually do it and see so that you don't forget what is covered here, right? So this power factor, once you know active and reactive powers, power factor is a straightforward issue. Then comes the reactive power. Reactive power is Vi sin phi. One way of looking at it, if you know cos phi, then sin phi is not very far away. Square root of 1 minus cos square phi is sin phi. So you already know apparent power, which is V multiplied by I. Multiply this with sin phi and you will get a reactive power. Then what next? This here you had an apparent power, power factor and reactive power. Now you have understood how to go about it. Then comes the question of frequency. But interestingly, we can go for the frequency and power factor in a different way, entirely different way. In that way, what you do? Let us see what to do. And here using sampling theorem you have done it, but we don't want to do sampling theorem. We don't want to do this. We want to do something different. It is this, it is this. Here I have added a term ZCD. It's a zero crossing detector. You can see it here on this graph. This is the voltage waveform. Voltage waveform is negative before this point, and it enters into the positive region here, remains in positive region here, and then it once again goes back into the negative region. So what zero crossing detector will do? It will see when the waveform crosses 0. And as soon as it crosses 0 towards positive side, it will give you a logic 1 output. And it will remain in the logic 1 output as long as the waveform remains above 0. At this point, it becomes logic 0. So it will swing from logic 1 to logic 0 as the waveform moves across the 0 line. What is true with voltage? Same thing is true with current. So you have another square wave, and this is related to the current waveform. It means if I can measure this time between this and this, then I know the delay between voltage and current. If I know the delay between them, and if I know the frequency, I can straight away find out the angle phi and therefore cosine of phi, right? So we actually measure phi, and then you can in your program you can mention how to get cos phi from phi. You may have a table, or you may have some expansion, trigonometric expansion to find out cos phi. One simple method is you say that okay, this is the time period T1, this is half cycle time period is T2, and T2 is equivalent to 180 degrees. T2 represents this time. This is same for current also, because they have the same frequency. Current is produced by voltage, and both of them are sinusoidal. So you can easily say that this is also the time of half time period of the current wave. So T2 is equivalent to 180 degrees. And so the phi is 180 degrees into T1 upon T2, which gives you 60 degrees. In this particular case, it is 60 degrees. If you know what is T1 and T2 in general, you can find out by this method. So you will know phi, and from phi, you can extract cos phi, right? And this cos phi may be more accurate for the reason than the previous method, for the reason that here you are not finding out Vi cos phi and then Vi cos phi and then doing the division operation as you have seen earlier. So here you had seen that you find active power. So there will be an error because there is always a tolerance. There is an error here also because there is a tolerance. And therefore, this operation, which again, which is going to yield this, will also have some tolerance. And therefore, cos phi using this method may be less accurate than the method we are just discussing. So this method is likely to be more accurate than the methods we used earlier. Now here you have, how will you measure this T1 and how will you measure this T2? So one method is when there is zero crossing detector changes this, it starts a timer. At this point, a timer is started. And if you want to be more accurate, then what you will do is, when this goes from 0 to 1, an interrupt occurs. And that interrupt starts the timer. Okay? So you will know, then the next is this one. When this comes, another interrupt comes, and then that interrupt reads the content of this timer. This is not causing any timer start, etc., but this did. So it started a timer, and when this interrupt comes, that interrupt will simply read the content of the timer. And then when it falls to 0, it will again read the content of the same timer. Okay, so you get T1 and you get T2. That's what we are going to do. So T1 upon T2 will lead you to cos phi as well as frequency, because then what will be frequency? Frequency will be 1 upon 2 into T2 and phi will be this. So you form a table and the table will create the value of cos phi for you, right? You look it up and you will find this. When you make a table, the precision will depend upon how many steps you have in the table. That is, what is the resolution of your table. Suppose your resolution is only 1 degree, then which means for 0 degree, what is cos phi? For 1 degree, what is cos phi? Like that, if you have made it, in that case, the resolution will be only 1 degree. And if you say that, no, I will have phi equal to 0, what is cos phi? Phi is equal to 0.5, what is cos phi? If you go like that, then your resolution will be 0.5 degrees, and accordingly you will get a proper cos phi. From this cos phi, if you derive sin phi, in fact, with this phi in the table, if you have sin phi values also, then as soon as you get phi, you also get cos phi and sin phi. This sin phi is again more accurate than the way you did it earlier. So friends, this is how we conclude our program. Here we have done all these things: reactive power, frequency, power factor, everything. So I conclude this installment here, and we will meet in the next episode. Until then, thank you, have a nice time, and